Monoidal categories and their representations, Lecture 17, Quantum Groups. Let us first recall the definition and finite dimensional representation theory of the Lie algebra SL2. The Lie algebra SL2 over the complex numbers is the Lie algebra of all traceless 2 times 2 complex matrices. This algebra has a basis consisting of the following 3 elements. The matrix E, which has 1 in position 1, 2, and the rest is 0. The element F, which has 1 in position 2, 1, and the rest is 0. And the diagonal matrix H, which has 1 and minus 1 on the main diagonal. As usual, the Lie bracket is given by the commutator of matrices. So the Lie bracket of x and y is the difference between xy and yx. We can write this explicitly in our basis. The bracket of any element with itself is 0. The bracket of E and F is h, and of course the bracket of F and E is in minus h. The bracket of E and H is minus 2e, and so the bracket of H and E is 2e. And the bracket of F and H is 2f, and so the bracket of H and F is minus 2f. So we have the Hopf algebra, which is the universal enveloping algebra of SL2. So this is the algebra which is given by the following presentation as the algebra. So it is generated by 3 elements E, F, and H, and the relations are just given by the previous table. So the bracket of E and F is equal to H. So EF minus FE is equal to H. The bracket of H and E is 2E. So HE minus EH is equal to 2E. And similarly, HF minus FH is equal to minus 2F. So this is a presentation of the universal enveloping algebra of SL2 as an algebra. As usual, we have that the category of all SL2 modules is isomorphic to the category of all USL2 modules. So any SL2 module has a unique extension to an USL2 module, and each USL2 module is canonically an SL2 module. And the homomorphisms are the same things. So the multiplication in this Hopf algebra is defined as follows. The comultiplication delta applied to E is equal to E tensor 1 plus 1 tensor E. The delta of F is F tensor 1 plus 1 tensor F, and delta of H is H tensor 1 plus 1 tensor H. So delta of any element of the Lie algebra is given by this element tensor 1 plus 1 tensor this element. The co-unit from USL2 to C is the unique algebra homomorphism which kills the Lie algebra, which means it kills the elements E, F, and H, which generate the universal enveloping algebra. And the antipode, it's a unique algebra anti-homomorphism from USL2 to itself, which sends E to minus E, F to minus F, and H to minus H. Recall now the finite dimensional representation theory of SL2. So since we have the Hopf algebra USL2, we have the tensor category of all finite dimensional SL2 modules. And by Weyl's theorem, we know that this category is semi-simple. So it's a fusion category. It's a semi-simple, rigid, monoidal category. So the simple objects in this category are indexed by non-negative integers. So if you have a non-negative integer k, we have the corresponding simple object v upper k. So this is a simple module which has dimension k plus 1, and it has the highest weight, so the maximum h eigenvalue, which is equal to k. So the index is actually the highest weight of this module. And the tensor product formula for the modules is as follows. If we tensor Vm and Vn, the outcome is usually decomposable, so it's a direct sum of simples. And here are the simples which contribute to this direct sum. So the maximal possible highest weight for a simple in this direct sum is m plus n. And then we should go down by 2. So the next one is m plus n minus 2, m plus n minus 4, and so on. all the way down to the last module appearing in this tensor product is given by the index the absolute value of the difference between m and n. So this monoidal category is actually a symmetric monoidal category with respect to the usual symmetric braiding, which is inherited from finite dimensional K vector spaces, where we just swap the components of the tensor product. Also recall that we have the following Schur-Weyl duality related to representation of SL2. Let us consider the simple module V upper 1. This is exactly the two-dimensional natural SL2 module. So SL2, this is an algebra of 2 times 2 matrices, and 2 times 2 matrices operate naturally on a two-dimensional vector space. This is exactly the simple module given by this action. For any m greater than or equal to 1, we can consider the m's tensor power of V1. And due to our symmetric monoidal structure, we have the natural structure on this tensor power of a module over the symmetric group Sm. So here a permutation sigma from Sm simply permutes components of the tensor product. So it sends the vector V1 tensor V2 and so on tensor Vm from this m-fold tensor product to the vector V sigma 1, tensor V sigma of 2, and so on V sigma of m. So on this m-fold tensor product, we have the natural action of Sm. Since we work with the Hopf algebra, this m-fold tensor product is of course also naturally a USL2 module. And this is a special case of the Schur-Weyl duality, which says that the actions of USL2 and the group algebra of Sm over the complex numbers on this m-fold tensor product of V upper 1, these two actions generate each other's centralizers. Now let us quantize this. So in the rest of the lecture, we will define a quantum analog of SL2. And this is a deformation of the universal enveloping algebra of SL2, which depends on a certain parameter, and which we will define and explore as a Hopf algebra. And then see how the representation theory of that algebra depends on the deforming parameter. So the parameter will be denoted by Q, and we take Q as a non-zero complex number, which is different from plus and minus 1. Now we define the associative and unital algebra over the complex numbers, which we denote by UQ SL2, via the following presentation. So it has generators capital E, capital F, and the capital K to the power plus minus 1. And it has the following relations. So k and k minus 1s are inverses of each other, so they multiply to 1. Ke is equal to q squared ek. Kf is equal to q to the power minus 2 fk. And the commutator of E and F, so EF minus FE, is equal to k minus k inverse divided by q minus q inverse. Some immediate consequences, so since k is invertible, we can multiply the second equation here by k inverse on the right and get that k inverse is equal to q squared e. So if we conjugate e by k, we get e, but with the additional factor of q squared. And similarly for f, we will get the additional factor q to the power minus 2. So this is the definition of the algebra UQSL2 as an algebra. So how do we compare this definition to the classical definition of USL2? We should think of the generator K as Q to the power classical generator H. Note that H is diagonalizable with integer eigenvalues on all finite dimensional SL2 modules. Therefore, if we take q to the power an integer, we will always get a non-zero complex number. Hence, it follows that the action of k will also be well-defined, diagonalizable, and invertible on all analogues of such modules. And the question is how to get h back from our k. Then one can use the classical limit that h is actually equal to the limit where q goes to 1 of k minus k inverse divided by q minus q inverse. How to see this? We can use the Taylor expansion for q to the power h. So this is the sum over all I greater than or equal to 0, h times the natural logarithm of q, the whole thing to the power I divided by I factorial. And now if you plug it in here and take this limit, then you will get h back. So in this sense, one can view the universal enveloping algebra of SL2 as the limit, in such a sense, of the quantum algebra UQSL2 when q goes to 1. Note that the definition of UQSL2 requires that q is different from 1, for otherwise this is definitely not defined. So the last relation doesn't make sense if q is equal to 1. So we start with the Poincare-Birkhoff-Witz theorem for this quantum algebra. So the claim is that the monomials of the form f to the power a, k to the power b, e to the power c, where a, b, and c are integers and a and c are non-negative integers, these monomials form a basis of our quantum algebra. The idea of the proof: as usual, the generation is easy, so given a monomial, we can use the defining relations in order to change the order of the factors in the monomial. And so we can rearrange this order such that we always get to an order which looks like this one. The expense, when we rearrange the factors, we will get monomials of the shorter lengths, and this we can deal with by induction. The trick is a linear independence, and in order to prove linear independence, one usually defines a representation of the algebra where all these monomials send some fixed vector of the representation to linearly independent vectors. To construct such a representation, consider the polynomial algebra in 3 variables x, y, and z. And let us localize the variable y. And we define on this localization the structure of the module over our quantum algebra using the following formula. So f acts simply by raising the power of x by 1. K acts on the monomial x to the power a, y to the power b, z to the power c by raising the exponent of y by 1. But also we have to compute k via all x's, which means via f's. So there is also a price to pay, which is the factor q to the power minus 2a. The action of E is complicated. So when we act by E at the monomial x to the power a, y to the power b, z to the power c, we get 2 terms. In the first term, the exponent of z is raised by 1, but we also have this additional factor q to the power minus 2b. And then we have the complicated second term. So here, first we have the coefficient q to the power a minus q to the power minus a divided by q minus q inverse. So this s is a typo, it should be a. Then x to the power a minus 1. Then we have y, q to the power 1 minus a minus y inverse q to the power a minus 1 divided by q minus q inverse times y to the power bz to the power c. And one can check that this definition satisfies the defining relations for our algebra. And in this module, the standard monomials send 1, obviously, to linearly independent elements in the standard basis. Therefore, the standard monomials are linearly independent to start with. And this proves this analog of the Poincare-Birkhoff-Witz theorem for the algebra UQ SL2. Next, let us briefly discuss zero divisors and the center, without many proofs. From the PBW theorem, it is not very difficult to deduce that the quantum algebra UQSL2 is actually a domain. It does not have zero divisors. And the idea of the proof is one should take two elements, multiply them, and track the leading term. The leading term we can now define using our standard monomials given by the Poincare-Berkowitz theorem. Similarly to USL2, we have the Casimir element, C, which is defined as Fe plus KQ plus K inverse Q inverse divided by Q minus Q inverse squared. And it is very easy to check that this element C belongs to the center of the quantum algebra UQSL2. And now we will have the first instance when we see the difference of how the quantum algebra behaves in the case when our parameter Q is not a root of unity. This is usually called the generic case, and how it behaves in the case where Q is a root of unity. So in the generic case, that is when Q is not a root of unity, then the center of our quantum algebra is a polynomial algebra generated by our Casimir element C. At the same time, when Q is a primitive else root of unity, where L is odd and is greater than or equal to 3, then the center of our quantum algebra is generated by our Casimir element C together with the else powers of all generators. So in other words, the center is much, much bigger than in the generic case. So now let us discuss the representation theory of this quantum SL2 in the generic case. So we assume that Q is not a root of unity. There is a standard notation for an integer m in brackets denotes the following fraction q to the power m minus q to the power minus m divided by q minus q inverse. So let n be a non-negative integer. So we denote by Vn plus the linear span of the elements Vi, where I is an integer between 0 and n. And we claim that on this vector space we can define the structure of the module over our quantum algebra in the following way. The generator K acts on Vi, so Vi is an eigenelement for K with an eigenvalue Q to the power n minus 2i. The generator F maps Vi to Vi plus 1 unless I is equal to n. So F acts on Vn and the output is 0. So F kills Vn, and for the remaining cases, Vi is sent to Vi plus 1. And the generator E, it kills V0, and for the remaining elements, Vi is sent to Vi minus 1 with the coefficient the quantum I times the quantum n plus 1 minus I. So this m in bracket is usually called the quantum m. And the claim is that these formulas define on Vn plus the structure of a simple UQSL2 module. Similarly, for a non-negative integer n, we can consider the vector space Vn minus with the basis given by Vi primes, where I is an integer between 0 and n, and we can define the structure of UQ module on this vector space by the following formulas. So Vi prime is an eigenvector for K with the eigenvalue minus Q to the power n minus 2i. F maps Vi prime to Vi plus 1 primed, and it kills Vn. And E kills V0 primed, and it maps Vi primed to Vi minus 1 primed for I greater than 0, with the coefficient given by minus quantum I times quantum n plus 1 minus I. So the claim is that these formulas also define on Vn minus the structure of a simple UQSL2 module. And then these two classes of modules, which are defined on this and on the previous slide, in fact, they exhaust all simple finite dimensional UQSL2 modules. in our generic case. So theorem, any simple finite dimensional UQSL2 module is isomorphic to either Vn plus or Vn minus for an appropriate n. And we also have an analog of Weyl's theorem. Any finite dimensional UQSL2 module is completely reducible. For more details on all these statements, I refer to the book of Janssen, which is called Lectures on Quantum Groups. Here in this book, all this is written with all details. Now let us briefly touch upon the representation theory in the root of unity case, just to show how different this is from the representation theory in the generic case. So assume that Q is a primitive else root of unity where L is odd and is greater than or equal to 3. For two complex numbers b and lambda, where lambda is non-zero, consider the vector space NB lambda with basis Vi, where I is between 0 and L minus 1. It's an integer between 0 and L minus 1. So the dimension of NB lambda is L, exactly this L. And now we define on this NB lambda the structure of the UQ module. So WI's are eigenvectors for k with the eigenvalue q to the power minus 2i times lambda. F operates in this basis as follows. F applied to Wi is Wi plus 1, if I is smaller than L minus 1, and F applied to WL minus 1 is B times W0. So now we have some kind of cyclic action, and then in one of the elements we have this additional factor B. And E operates as follows. So E kills W0, and for other I, EWI is WI minus 1, with the additional coefficient quantum I times lambda q to the power 1 minus I minus lambda inverse q to the power I minus 1 divided by q minus q inverse. And the claim is that this defines on NB lambda the structure of a module over our quantum algebra. And if B is non-zero or lambda to the power 2L is not equal to 1, then this module is simple. So we have a family of simple modules depending on two parameters given by complex numbers. Completely different behavior than in the generic case. And then one can actually classify all simple finite dimensional modules in this root of unity case. The modules which you see now on the screen, they contribute to this classification, but there are more, and I refer to Janssen's book for full details. So the idea here is just to show you how many more modules we have in the root of unity case. So now we have discussed UQSL2 as an associative algebra. Let us go further in the definition of it as a Hopf algebra. Let us define the comultiplication. So for simplicity, we now denote the quantum algebra UQSL2 simply by U. Proposition: there is a unique algebra homomorphism delta from U to U tensor U, which sends E to E tensor 1 plus K tensor E, which sends F to F tensor K inverse plus 1 tensor F, and which sends K to K tensor K. Proof: so we just need to verify the defining relations for the images of the generators. For example, let us check the most non-trivial defining relation, that EF minus FE is equal to K minus K inverse divided by Q minus Q inverse. So using the formulas which we have, delta of E delta F minus delta F delta E equals the following expression. So delta of E is E tensor 1 plus K tensor E, delta of F is F tensor K inverse plus 1 tensor F, and now we swap them. This we can compute, and we have this very big formula where we just naively multiply the ingredients here. And now we see that E tensor F and minus E tensor F just cancel each other. And also, which is less trivial, that these two terms cancel each other. This is explained here. So Kf tensor Ek inverse and Fk tensor K inverse E, they cancel out, because Fk is equal to Q square Kf, and Ek inverse is equal to Q square K inverse E. And with this minus sign, these two cancel each other. So what remains is exactly EF minus Fe tensor K inverse plus K tensor EF minus Fe. So now we can use the defining relations for our algebra and plug in here K minus K inverse divided by Q minus Q inverse, and similarly here. Then we will have this expression, and here K tensor K inverse and minus K tensor K inverse also cancel in the numerator. And what we get is K tensor K minus K inverse tensor K inverse divided by Q minus Q inverse. This is exactly delta of K minus delta of K inverse divided by Q minus Q inverse. So that is exactly what we needed. The claim is that this comultiplication, which we defined, is coassociative. Proof? Again, it's enough to check this for the generators. So let's check it on the generator E. So the left-hand side, so we take E, apply delta, and then delta tensor the identity. So this is delta tensor the identity applied to E tensor 1 plus K tensor E. So this is delta of E. If we take that delta tensor the identity, we get E tensor 1 plus K tensor E tensor this one. And here we have K tensor K tensor E. Similarly, the right-hand side is identity tensor delta applied to E tensor 1 plus K tensor E. When we apply this to the first component, we have E tensor 1 plus the second component K tensor, E tensor 1 plus K tensor E. And now we compare these two. So we have E11, E11, KE1, KE1, and KKE, KKE. So these coincide. And similarly, we can check it for all other generators. So our comultiplication is really coassociative. Now let us define the counit. Proposition: there is a unique algebra homomorphism epsilon from U to C, which kills E and F and sends K to 1. So the existence follows from the fact that such an assignment preserves the defining relations. We can just check the defining relations. And the uniqueness follows from the fact that we have defined the map on the generators. So this is straightforward. And the claim is that the following two diagrams commute. If you start from U, we use a comultiplication, and then we go to U tensor U, and then we use the epsilon on the second component, we get to U tensor C, and then we have the canonical isomorphism to U. So this diagram commute, and similarly for the applying epsilon to the first component. And again, to prove these diagrams, we just need to compare the images of both maps in the diagrams on the generators. This is a straightforward exercise. Finally, let us define the antipode. Proposition: there is a unique algebra anti-automorphism S from U to U, which sends E to minus K inverse E, which sends F to minus Fk, and which sends K to K inverse. To prove existence, we again need to check the defining relations for the images of the generators. For example, if we take the relations that EF minus FE is equal to K minus K inverse divided by Q minus Q inverse, then this should be sent to the relation. Note that this is an anti-automorphism. So S of F times S of E minus S of E times S of F. We plug it in. We get minus Fk times minus K inverse E minus the product in the opposite order, which is equal to Fe minus K inverse EFK. When we move K inverse over E, we have a price, but then over F, we pay the opposite price, so these cancel others, and we get Fe minus EF, which is equal to K inverse minus K divided by Q minus Q inverse, exactly what we needed. And all other relations are checked similarly. So this proves existence, and uniqueness follows from the fact that the map is defined on the generators. One can actually check that the square of this antipode, this is now an automorphism of U, that this is given by conjugating by the invertible element K. So now we claim that all the above definitions define on UQ the structure of a Hopf algebra. For this, we need to check the big hexagon diagram for the antipode. And this splits into two square diagrams. So the first one, we start with U, we co-multiply, then we use the antipode on one of the components, and then we multiply. And this composition should be the composition of epsilon and eta. And similarly for using the antipode on the other component. Again, we only need to check the whole thing on the images of the generators. It is easy to see that both diagrams send k to 1 and e and f to 0. So here is an example for e. E we co-multiply to e tensor 1 plus k tensor e. Now we use the antipode at the second component. So here 1 doesn't change, e tensor 1, but e we go to minus k times k inverse e. And now when we multiply, the first gives e, and k inverse cancel each other, and then minus e, we get 0. And similarly for the other diagram. So if we put all this together, we get the corollary that our algebra U, together with the unit element eta, our multiplication m, the comultiplication delta, the co-unit epsilon, and the antipode s, is in fact a Hopf algebra. Let us now exemplify the use of the Hopf algebra structure to look at the powers of the natural module. Assume that we are in the generic case, so Q is not a root of unity. Then we have the natural U module, which is the module V1, plus. So it has a basis consisting of two elements, W and V, and the action where E acts as the matrix E with 1 in position 1, 2. F acts as the matrix with 1 in position 2, 1. And K acts as a diagonal matrix with Q and Q inverse on the diagonal. The second power of V has then the basis given by the tensor product of W with itself, then W tensor V, V tensor W, and V tensor V. And then in this basis, K acts via the following diagonal matrix, and we have Q squared, 1, 1, and Q minus squared on the diagonal. E acts as the following matrix, 0, Q1, 0, 0, 0, 0, 1, 0, 0, 0, Q inverse, 0, 0, 0, 0. So this Q appear because in order to define the action of E on the tensor product, we need to use the comultiplication. And then there will be some K, so K inverses appearing, and K acts as Q or Q inverse. So this is why we have this Q and Q inverse appearing here. And similarly, F acts via the matrix 0, 0, 0, 0, 1, 0, 0, 0, Q inverse 0, 0, 0, 0, Q, 1, 0. And then it is easy to check that the following matrix defines an endomorphism of the second power of the natural module. So this is a matrix given by Q inverse 0, 0, 0, 0, 0, 1, 0, 0, 1, Q inverse minus Q0, 0, 0, 0, Q inverse. Note that if you plug in Q is equal to 1, we will get 1 on the diagonal, 1 on the diagonal, and this will be 0. So this is a matrix which swaps the second and the third basis elements if Q is equal to 1. But if Q is not equal to 1, this is quite a non-trivial linear operator on the vector space. And now we can slowly come to the quantum analog of the Schur-Weyl duality. So consider the m's power of the natural U module, V. So define Ti as the linear map on this m's power. So here I is some number between 1 and m minus 1. So the map Ti is given by first taking the I minus first power of the identity. Then we apply our map theta. This is an endomorphism of the second power of V given by this matrix. And then the rest is again given by the identity, the action on the remaining factors. Then from the previous slide, it follows that this belongs to the U centralizer of the m's power of v. It is easy to check that these linear operators Ti satisfy the following relations. So the eigenvalues of Ti are Q and Q inverse. This actually follows from here. The distant Ti's which are not neighborings of each other, they commute. So Ti Tj is equal to Tj Ti if I minus j is greater than 1. And Ti and Ti plus 1, they satisfy the short braid relation. So the algebra with the presentation given by these relations is actually called the Hecke algebra. And so we have the action of the Hecke algebra on our m-fold tensor power of v. So in fact, it's not the full Hecke algebra which acts here, since v is two-dimensional. This action factors through a certain quotient of the Hecke algebra, which is called the temporally Lieb algebra. And we have the quantum Schur-Weyl duality, that the actions of u and the Hecke algebra on V tensor M generate each other's centralizers. Okay, let us finish with some problems and questions. Question 1. Prove with all details the Poincare-Birkhoff-Witz theorem for the quantum SL2. Question 2. Prove that UQSL2 is a domain with all details. Question 3. Prove the following formula for the comultiplication applied to e to the power r. So this is a sum, I from 0 to r, q to the power I times r minus I, and then the product of quantum r minus 1, and so on, quantum r minus 1 plus 1, divided by the quantum I factorial, and then e to the power r minus I, k to the power I, tensor e to the power I. Question 4, check with all details that delta is coassociative. And question 5, prove quantum Schur-Weyl duality for SL2. Thank you very much and see you next time.